Hello everyone, I hope you are doing well. In this video, I will discuss the hidden potential of parity-time high-contrast gratings as a new platform for integrated thin-film gas sensors. The carbon dioxide and methane and other pollutants that we release every day into the atmosphere act as a blanket, trapping the sun's heat and causing the planet to warm. We know this phenomenon as the global warming. The global warming is one of the most dangerous issues which the humanity is facing with, can cause more severe weather, in a way that wet areas become wetter and dry areas drier. Also, today's scientists point to climate change as the biggest global health threat of the 21st century. Extreme heat kills more Americans each year on average than hurricanes, tornadoes, floods, and lightning combined. In the same way, the heat can affect other species and increase the extinction rate. The high rate of absorption caused by global warming makes the oceans more acidic and change the marine ecosystems. Also, rising sea levels threat low-lying areas, including New York, Los Angeles, and Miami. So, providing an effective method to detect and control greenhouse gases is extremely important today. Due to the molecular vibration, a variety of greenhouse gases, such as methane, can absorb mid-infrared radiation at a specific wavelength, generating an absorption fingerprint. You can see the absorption fingerprint I'm talking about. Hence, each gas can be detected through its spatial absorption pattern. These mid-infrared gas sensors have a variety of applications in different areas, such as disease diagnosis, manufacturing control, environmental monitoring, national and national security surveillance. Compared to electrochemical sensors, optical sensors using non-destructive methods show lower maintenance costs, longer lifetime, higher stability, and faster response. With that being said, it seems that optical sensing can be that effective method we are looking for. Commonly, each optical gas sensor consists of three parts: a light source, an interaction path, and a detector. Using photonic structures in interaction volume can enhance the light-matter interaction significantly. If we can design an active photonic structure which can play as light source and enhance the light-gas interaction at the same time, the device size can be reduced notably. Our suggested material to achieve this goal is PBSE or lead solenoid nanocrystallized films, indicating photoluminescence radiation around 3.3 micron. This wavelength is matched with the feature absorption peak of methane. To deposit PBSE nanocrystals as an active material, we suggested the low-cost and simple method known as chemical-based deposition or CBD. Commonly, CBD method leads to forming non-oriented and low-quality crystals known as IBI nanocrystals. Here you can see an SEM photo of an IBA sample. However, controlling the deposition condition in a special way can lead to forming different kinds of nanocrystals, named oriented attached nanocrystals, or OA nanocrystals, that you can see its macroscopic photo. This nanocrystal shows high quality and radiates at lower wavelengths. This figure shows the deposition path forming OA nanocrystals. This new CBD method to synthesize high-quality nanocrystals on amorphous substrate such as glass has been published in one of the well-known journals in this area, Journal of Material Chemistry C. After exploring the potential active material to fabricate the integrated on-chip sensors, we need to introduce an efficient platform for gas sensing. High-contrast gratings can be the potential optical platform we are looking for. This figure shows the schematic view of a high-contrast grating. High-contrast gratings are periodical structures consisting of low and high-index materials. Here, silicon is the high-index material and air is the low-index material. This figure, the part A, shows the confined electric field over the grating layer, where carbon dioxide gas is injected. This trap field increases the light-matter interaction in a short interaction path. The part B shows the absorption, the light absorption with HCG and without HCG. The blue curve is with HCG and this red line is without HCG. 300 times absorption enhancement was observed when we used HCG in the interaction path. So this microsized structure is a powerful platform for fabricating on-chip sensors. Recently, it is indicated that using active materials such as PBS in nanocrystal thin films to design optical components can add new interesting properties to the system. One of these properties is parity-time or PT-symmetry, which I will explain it in the next slide. Parity-time symmetry, rooting in quantum physics, was introduced first time in 1998. This theory says that non-Hermitian systems, which are invariant under time inversion and parity operators, can have real spectra. Due to the analogy between the Schrödinger equation and Maxwell's theory, this concept and its resulted effects were shown in 2010 on a coupled optical waveguides, which one of them shows the gain and the other one shows the exact same value, but this one is loss. The related Hamiltonian for these systems is shown here, where omega is the real frequency, kappa is the coupling coefficient, and plus minus gamma is the gain and loss respectively. The related eigenvalues shown by omega plus minus. These eigenvalues can be totally real if the coupling coefficient is larger than gamma, known as PT-symmetry regime. Once the coupling coefficient and gamma show the same value, two eigenvalues and eigenvectors will be united and make the exceptional point. While coupling coefficient is smaller than gamma, the system shows partial imaginary spectra, named PT-symmetry broken regime. Depending on the operation regions, the PT-symmetric systems show exciting properties like single-mode lasing and unidirectionality. The promising results given by PT-symmetric structures inspired us to combine HCG platform with parity-time symmetry concept to design a new active structure for gas sensing. We call this new structure PT-HCG. Here you can see a schematic view of the PT-HCG that we suggested on silica substrate, where n dot is the real refractive index and gamma is the imaginary refractive index. The active HCG or PT-HCG, similar to a passive HCG, it's dependent on grating thickness and grating period. However, in this active structure, the amount of introduced loss and gain plays an essential role. According to the PT-symmetry theory, by increasing the loss and gain contrast, PT-symmetry will be broken and field distribution will be changed from a symmetric profile to an asymmetric profile. We can see this process over one unit cell. In PT-symmetry broken regime, there is a point at we found a super intense field. Super intense, that's the amplitude of that field captured. We found a super intense field capturing in the gain area, and we called this point as a critical point or CP point. This phenomenon leads to a huge diffraction efficiency enhancement. You can see this enhancement here, where the diffraction efficiency enhanced from 25 to 2 multiple and 10 to the 6th power. The mechanism behind this non-trivial diffraction efficiency enhancement comes from the unusual behavior of PT-symmetric structures as scattering systems. A scattering matrix which relates the input and output fields is always unitary. This unitary condition forces unimodular S-matrix eigenvalues for passive structures, showing no imaginary part. However, in a PT structure, the unitary condition can be satisfied in two ways: by unimodular eigenvalues which are related to the PT symmetry phase, or by reciprocal eigenvalues associating the PT symmetry broken phase. So once one of these eigenvalues approaches zero, its reciprocal counterpart approaches infinity. However, their product remains unitary. Once the system reaches the critical point, due to the capturing the mode with infinity amplitude in the gain areas, the intensity of the confined field is significantly increased. That is why we see a huge diffraction efficiency enhancement at the CP point. Diffraction efficiency enhancement in theory can reach to 10 to the 6th power, which is promising. And we can use this structure as a powerful light source for integrated on-chip sensors. The fabrication and providing more comprehensive theory for the presented results are the next step that will be done soon. Thank you for your attention, and I'm ready for any question. And here you can find my email address.